Welcome to our viewers and our listeners. This is episode 6 of Light Conversation. My name is Philip Constantine. We're joined also by James Portman. Welcome, James.
Hi, Phil. Hi, everybody.
Looking forward, yes, very well, thank you. Looking forward to today's topic. We're discussing the conversion of photons to electrons and in reverse. Very interesting topic, and love to see what we can learn from you today, James.
Yeah, it's one of my favorite subjects because I think it is one of those defining moments of physics and engineering that makes the difference between a product like the Lidar actually working and it becoming nothing more than an expensive hobby. So, I'm looking forward to talking about this.
Great, thank you. So let's kick this back to Physics 101, energy. The law of conservation of energy states that you cannot create or destroy energy, and energy can only be transformed from one form to another. So how does an electron become a photon, and how does a photon become an electron? If we consider these principles of transformation of energy.
Unfortunately, when you look at physics can apply at many different levels. You can apply it at a macro level, and you can just look at the overall effect, or you can apply it right down to the quantum physics level. And each of these explanations, they're reasonable. They make sense. The maths looks good. Maxwell had a great time with this. Einstein had a great time with this. But as engineers, we tend to prefer the practicality aspect of it and say, well, can it actually be done? Can you convert an electron to a photon? And the answer is, as usual, yes, but. And it's the but that is the more interesting part of the discussion rather than the actual physics and the transformation that takes place. Because we can talk about electrons, whizzing around atoms, and photons, whether they're particles or waves and so on. But in the end, these are only analogies. Then they don't necessarily represent what's really happening. So as engineers, we try not to get too bogged down in these analogies, and instead we rather say, well, what is the net result? I want as many photons as I can get for as little electricity as I can put into it. So it's this conversion efficiency that actually becomes far more important. And of course, anything that doesn't become photons becomes heat. And heat management becomes an essential part of any electronic circuit design, for example, because you have to keep the thing cool. So in an ideal world, you would want electrons with a certain amount of energy to produce photons with exactly the same amount of energy and 100% conversion. This just does not happen. And in fact, surprisingly, conversion efficiencies tend to be horribly low. So even though the laws of physics might say, oh, you can achieve what's known as a certain quantum efficiency, it doesn't mean in practice when you build a device to convert electricity into light, for example, or to convert solar energy into electricity, that conversion efficiency is easily achieved. In fact, it turns out to be incredibly difficult to achieve high conversion efficiencies. I guess the real question is, though, does it matter? Because what we've spoken about in the past is looking at certain characteristics that are important to us. In the case of a LiDAR, for example, what you want is a bright flash of light. Now, as long as I get that bright flash of light, does it really matter how many electrons I had to throw at it to produce that flash of light? Well, if the heat dissipation is so high that the laser producing the light melts, then yes, this is a bit of a problem. And, whilst we can use liquid hydrogen cooling, this is not a cheap way of designing a nice, efficient laser system. But if, in fact, the energy penalty is small enough to be tolerable, then, in fact, we don't care that much about the conversion efficiency. We just care that we're getting enough energy out. So to give you a typical example, a pulsed laser diode, when I built my first LiDAR systems, we were looking at putting roughly 2 kilowatts of peak power into a pulsed laser diode in order to get about 10 watts of light out. So you can see the conversion efficiency is horrible, but it didn't matter because we only cared about those 10 watts. We didn't care about the 2 kilowatts.
So let's maybe take a very simple example. If we look at solar panels, for instance, I mean, we have light hitting a solar panel, and those are photons, and that then transforms the light energy into electrical energy. But the electrons are already there. So how does the electron change, or how does the state of the electron change as this photon hits the electron, to be able to then, at some rate of conversion, be able to transform that light energy into electricity.
Yeah, and if it was a simple answer, I guess we would have super efficient solar cells, and we would have super efficient photon detectors, but we don't. And the reason is because the conversion efficiency is not necessarily a simple conversion efficiency. It's not just about one photon creating one electron.
Yeah.
So to give you an example, if you have something like a photon multiplier tube as opposed to a solar cell, what happens there is you can pre-energize the tube so that a single photon actually presents a complete avalanche of electrons. It can produce millions of them.
Oh, right.
But if you look at the physics, the conversion efficiency from a photon to an electron is only about 50% if you get it 100% right. So what that means is that there's a limit to how efficient you can be. In the case of solar panels, if you're looking at 20% conversion or higher, that is absolutely world-class. But when you're looking at solar panels, you not only have light available, but you also have heat available, and you have lots of different frequencies available. So what if you could convert each of those frequencies with higher efficiency and combine the net result? Well, in theory, what it means is you can make incredibly efficient and incredibly high-performing solar cells.
This is an interesting point because, if we consider for a moment the wave model of light as opposed to the particle theory of light, originally the prediction was, well, if we increase the light amplitude, we would increase the kinetic energy of those photons that are emitted, and then by increasing the frequency, I would increase the measured current, right? But of course, if contrary to those predictions is what we've actually proven to be true. So actually increasing the frequency increases the kinetic energy. So maybe just talk to us around amplitude and frequency.
Yeah, again, it's a difference between the laws of engineering and the laws of physics. I think these things are very easy to misinterpret. For example, whilst the particle model versus the wave model are useful from a mathematical perspective, sometimes in practice, it's a complex interaction that's actually taking place. So I'd like to throw in, just a twist on this. The assumption is that with something like a solar panel, you can treat the photon energy as a continuous stream of energy because the sun is shining down. But in the case of a device like the Lidar, this is not true. It's not a continuous stream of energy. It's a burst of energy. Now, does this temporal difference change the way that the conversion efficiency behaves at the macro level? We know it doesn't change it at the quantum level, but does it change it at the macro level? And the answer is absolutely. And it has to do with the physical manifestation of the conversion device. In other words, what does your detector look like? In the same way as what does your laser look like? That changes the conversion characteristics from electrons to photons. So one of the most surprising things that I discovered was that the conversion efficiency can drop off dramatically when you have high-speed waveforms, in other words, pulses. So a standard detector that you can buy from your local electronics store has very high conversion efficiency on continuous light shining upon it. And you can rely very much on that. It's nice and linear. It's a gorgeously sensitive and a gorgeously capable device. The moment you give it a flash of light that's only a few nanoseconds long, you get nothing out, nothing at all. So what happened to the conversion efficiency? It turns out that some of the macro phenomena have begun to dominate. And these macro phenomena are things like capacitance and electron mobility, resistance, inductance down wires, and so on. And normally we think of these as tiny, tiny little phenomena. A typical pin photodiode can have a few picofarads or even half a picofarad of capacitance. And we think, oh, well, that's nothing. That really doesn't add up to anything. But it does when you're working at the speed of light. It does when your edge transitions are in the order of nanoseconds. And what that means is that if you're trying to design a system which is going to detect photons of light, you can't simply look at the efficiency of your detector. You have to look at the speed characteristics as well. And in the end, even if you have a relatively insensitive detector that's very fast, chances are you'll get a much bigger signal than if you have a very sensitive detector that's slow.
So you describing a almost an inertial lag kind of hysteresis effect that is inherent within these sensors. Are we able to account for that? Is it a constant across different time periods, across different wavelengths, across different measuring distances? Is it a basic offset that you take into account in the design of the product? Or is it a moving target in terms of having to adjust for these capacitive and inductive lag effects that result off the sensor?
Again, it's one of these things that it depends how deeply you look at it. To a first order of magnitude, you may say that the same type of sensor behaves in the same way. And, that's cool. That's good enough. But when you say, I want to measure how far away something is with an accuracy of, let's say, 1 centimeter or 1 millimeter, suddenly these second order phenomena that are beginning to dominate have enough variability that even from one detector to the next of an identical type from the same wafer run, that there is a significant difference in the performance. There is a noticeable difference in the performance. So in fact, one of the early lessons we learned in the Lidar game was that you have to characterize your detectors. Whether it's a photomultiplier tube or a pin diode or an avalanche photodiode, it doesn't matter what type of device it is. You can't just rely on the manufacturer's specification sheet to say, I know what the specs are, therefore I can build a circuit to make it work. What you have to do is to build the entire conversion and amplifier chain and then characterize that chain so that you understand precisely which elements remain constant. For example, distance is often one of those characteristics which is what they call agnostic. In other words, it doesn't have any direct effect on the performance of the sensor because the sensor doesn't know how far away the photons came from. All it knows is that a photon has arrived. But the intensity of the amount of light falling on it can make a huge difference, and the speed at which the light falls on it can make a huge difference. So you definitely cannot neglect these effects, and you have to find a way of eliminating them if you want to make a precision device.
Right, that helps. So when selecting a sensor for a LiDAR device, what are the different characteristics that you consider as a design engineer? If you pick up a typical spec sheet for a sensor, what are the things you look for, and what are the pitfalls? What are the things you try and avoid when selecting a sensor for design?
This is such a wonderful question because it is the very essence of engineering, and that is, how do you get the most out of a system? And usually, whenever you get more of something, let's say more light out, there's a price to pay. And I don't just necessarily mean dollars. There is a price to pay in, for example, an increased noise level that goes with it. I remember hearing the analogy in Formula One racing cars where the whole aim of the game was to try and improve downforce. But the problem is, every time you increase the downforce so you could go through the corners quicker, you also increase the drag.
Yeah.
And it was the discovery of the ground effect that allowed them to have more downforce without increasing drag. Now, as an engineer, this is kind of the sort of thing we're looking for all the time. In other words, can we get more sensitivity out of our detector without adding more distortion or errors into the system or temperature drift or variable phenomena? And there are very few devices that do this for you. I can tell you that I have favorites. So whilst most people look at a pin photodiode and they say, on paper, this is the best signal-to-noise ratio device you can get, I don't like it because by the time you've added the amplifier chain, what comes out the other end tends to be very noisy. On the other hand, a photomultiplier tube is just fantastic because it converts a photon to an electron, and then that electron generates more electrons, and then that one generates more electrons, and you haven't amplified anything yet. This is all happening inside the photomultiplier tube. The only drawback is photomultiplier tubes are large and heavy and need high voltage power supplies and are difficult to operate. So we nearly got something for nothing, but we ended up having to pay a penalty. Yeah. So my preference is to pitch in the middle between the two in a device that's called an avalanche photodiode. So this is a semiconductor device that behaves like a photomultiplier tube. And what it allows you to do is that the conversion efficiency from a single electron to a single photon is still around 0.5. In other words, you need 2 photons to generate 1 electron. But it then has an amplification characteristic which will amplify that result typically by a factor of 100. Now, at that point, what it means is you get 100 times larger signal to start with than you would have done with a pin photodiode. And now you can feed that through your amplifier chain, knowing that the signal-to-noise ratio is good, that the speed is good, that the distortion is low, and that your characteristics are highly repeatable and predictable. Of course, I have to say this. So why doesn't everybody use avalanche photodiodes? And the answer is, it turns out there is a price to pay because you'd never get something for nothing. And avalanche photodiodes vary enormously from one to another in every single characteristic. And what that means is that you have to have a method of calibrating out or at least understanding and controlling the characteristics of an avalanche photodiode. This is very, very difficult. And it's what makes the design of LiDAR systems so hard.
And obviously an important factor as one needs to design a system that's eye safe and not having to pump huge amounts of energy through the laser beam, being able to do that amplification at the receiver stage obviously allows you to maintain your eye safety rating.
Yeah, and that's critical. Again, it's one of the reasons why you do want a very efficient detector if you can get it. And of course, apart from the difficulty of managing these efficient detectors, there aren't many companies that make them, and they are expensive. Yeah. There's no shortcut to it. I'm kind of hoping the day will come when they're produced in such high volume that the prices will come down to something similar to a pin photodiode, but you're typically looking at 100 times the price, something in that order.
Right. Thank you. Thank you, James. I'd like to maybe take next week's conversation around eye safety and having us understand the different characteristics of beams and what makes LiDAR eye safety and what are the different changes that you can implement to ensure that LiDARs remain eye safe. Because some of these beams, go hundreds of meters, and how are you able to cram all of that into a tiny form factor? But not have customers go blind. You think this is a good topic?
Absolutely. It's really critical. And I think a lot of people tend to neglect this field, but I'll be delighted to talk about it. It's a very important subject.
Great. Thank you so much. Thanks for your time today, James. To our watchers on YouTube, please hit the subscribe button and join us next week for a discussion on laser beams and eye safety and what are the things we do to keep LiDARs eye safe. Thank you for your time today.